I'm a professor of computer science at MIT, and I'm the guest editor of the special issue on cache coherence in IEEE Computer. This particular talk that you're going to hear is titled Tailoring Hardware Coherence to Custom Fit Applications, and the authors of the corresponding paper are Arvind Sriraman from Simon Fraser University, Hongju Zhao, and Sandhya Dwarkadas from the University of Rochester. Sandhya, my understanding is that you were going to present the work, so please go ahead.
Thank you, Srini, for giving us the opportunity to present our work in Computer Magazine. I'd like to first introduce my co-authors and collaborators, both former students of mine and alumni of University of Rochester. Arvind Sriraman has been on the faculty at Simon Fraser since January of 2011, and he has been the initiator and close collaborator on a lot of this work since while he was a student and continuing through his time at Simon Fraser. He also continues to conduct other research in the coherence domain, in particular for GPU architectures. Hongju just defended his dissertation in August and joined NVIDIA. The work described in this paper and that I'm going to be talking about is largely covered by his dissertation. Over the last 10 years, the increasing number of transistors available with each new technology generation have been utilized to add larger numbers of cores, with the result that in the last year, manufacturers have introduced chips with close to 100 cores. For example, the 72-core Tilera GX72 and the approximately 60 cores on the Xeon Phi from Intel. And of course, the prediction is that the core count is going to continue to increase. There are several challenges to be addressed in utilizing these increasing core counts effectively, and foremost among them being reducing the need for off-chip bandwidth and streamlining intercore communication. A hardware coherent memory space is seen as desirable, but it comes at a cost. It comes at a cost in terms of metadata storage. It comes at a cost in terms of complexity, in terms of bandwidth, energy consumption, and extra communication latency, and these are all potential extra costs. If you look at these large core count processes, typically coherence is maintained using directories to avoid the high bandwidth costs of broadcast-based protocols. However, conventional directories still suffer from overhead, in particular large metadata storage needs and unnecessary traffic. And I'll focus first on the metadata storage needs. And if you look at the conventional directory-based protocols, taking a full map directory protocol into account, you'll see that in order to keep track of which cores actually cache data, the directory maintains a bit vector with 1 bit per core indicating whether the core actually shares the data for each cache line in the shared cache. This means that the overhead is a function of both the number of cores as well as the number of shared cache lines. So we made a very simple observation in that, as in this illustration you see, we have 3 cache lines that are shared by exactly the same set of cores. In fact, the blue, the red, and the dotted tags have the identical cores in their sharing set, and so the directory, in fact, duplicates this information in 3 entries. If possible, it would be great if we could get rid of this information. And based on this observation, we went looking at how many sharing patterns actually exist in different applications. Across a range of applications, 16 cores, and at 16 cores, remember, there's a possibility of 2 power 16 possible sharing patterns, so 65,000 sharing patterns. We actually see a maximum of about 2,000 in any given application in a snapshot of the application. And in fact, a typical number is closer to a few hundred. So based on this observation, we came up with a design that we call space or sharing pattern-based coherence, with the idea that we want to provide the ability to keep only 1 copy of any sharing pattern that's exhibited by the application. And in fact, represent in hardware only those patterns actually present in the applications at any given time. And so the way we do this is with a level of indirection. We create a table that's dynamically populated that contains the actual sharing patterns in the application. And the individual cache lines in the shared cache then point to the entries in the directory table to indicate what the sharing pattern is for that particular cache line. As I mentioned, this directory table is actually dynamically populated, which means that as the cache line is requested by different processes, the directory table sharing patterns are updated to represent what is actually being seen in terms of sharing within the application. Of course, there are several challenges to this, and those challenges include trying to make sure that the number of conflicts that exist in the table are minimized, trying to recycle entries when they're no longer used, as well as trying to determine what to do when the capacity of the table, which the capacity could potentially be exceeded, given that it is finite size, when that capacity is actually exceeded. And the key ideas here are that we actually gracefully degrade, and they gracefully degrade not just for all possible patterns, but for the specific pattern where we would have to introduce any inaccuracy. So to provide an overview of what we actually gain with the space implementation, we look at the directory size or the metadata storage requirements as we increase the number of cores. The first few numbers here are actual experimental evaluation, and the last couple are an extrapolation based on our prediction of the actual space requirements for the directory. As we can see, and remember that the scale that we're looking at in this graph is actually a log scale on both sides. As we can see, the full map directory, in fact, at 128 cores, requires 32 megabytes just for the directory. In other words, 128 cores implying that there is 128 megabytes of shared cache in this particular instance. So 25% of the shared cache size is required for the full map directory. Whereas for space, we require only 2.5 megabytes of storage, which is about 2% of the shared cache space. So you can see there's a considerable reduction in the directory size without a loss of much precision in the case of space. So we now turn to the second issue that we raised. Like I said, there are many challenges, and this is the second that we're trying to address, which is that of unnecessary traffic. This unnecessary traffic is usually because in typical directory-based protocols, and in fact in typical cache designs, the granularity for storage, for communication, and for coherence metadata is a fixed unit, and that fixed unit is typically the cache line size or the block size. In this illustration, what you're looking at is, in any particular cache line, the grayed blocks represent words that have been accessed by the core, whereas the unshaded blocks represent words that have not been utilized prior to eviction or invalidation at that core. Those unused words or unutilized data represent unnecessary traffic. And so our goal is to try to eliminate that unnecessary traffic, which we were able to do with a family of protocols we call Protozoa, which decouples the granularity of storage, communication, and coherence from the granularity at which the directory metadata is actually maintained. And by doing so, is able to improve the efficiency of the overall coherence protocol. Memory is treated as contiguous fixed-size regions. And when the first access to a particular region is made, the region is brought into the shared L2 cache and in its entirety. Now, the individual cores allow variable granularity and, in fact, predict the granularity of spatial access by the particular core based on past invalidations and evictions. And so, based on this prediction, core on the left realizes that all it needs are the red and the beige blocks. So the red and the beige blocks are requested, and the directory marks the particular core as caching this particular region in its metadata. The core on the right predicts that it needs the blue blocks, and so the directory correspondingly notes that it is a sharer and sends those blue blocks to that particular core. The specific regions, the specific blocks within the region that are cached by the individual cores may be disjoint or may be overlapping. But the key thing that Protozoa allows us to do is to avoid false sharing-based communication altogether in some instances. Here's a look at a typical and a very common idiom used in parallel programming where one might have an array of counters, and the individual cores access counters within this array in a fashion where core 0 accesses counter 0, core 1 accesses counter and 1, and so on. These counters happen to reside in the same cache line, but in fact, no true sharing actually occurs. In the baseline directory-based messy protocol, what results is the fact that every write by either core 0 or core 1 will result in an invalidation of the entire cache line in the other core and a movement of data from one core to the other in this fixed granularity of the entire cache line. With the Protozoa protocols, and specifically moving to the Protozoa multiple writer protocol, what we're able to do is to completely eliminate any traffic whatsoever by, if the data that is accessed by core 0 and core 1 are actually retained in the cache. Firstly, core 0 and core 1 each correctly predict that they will only access specific counter 0 and 1 respectively. Based on that, those are the only values that are actually stored in the cache. At the same time, those are also the only values that are communicated from the shared L2 to cores 0 and 1. When core 0 or core 1 actually writes the data, the invalidation indicates the specific words that need to be invalidated in the other cores. Once the invalidation is received, as long as the data is continued to be cached by the individual cores, no further traffic is generated. So in other words, Protozoa multiple writer allows multiple readers and writers to just disjoint words coexist in the cache. Protozoa essentially reduces the coherence traffic by avoiding false sharing via adaptive coherence granularity, reducing bandwidth requirements via adaptive communication granularity, and actually also reducing misrate not only by eliminating false sharing, but by increasing the storage capacity via adaptive storage granularity based on the type of adaptation that is used at the L1 core. So you can see from this graph that for some applications, those that might incur intensive false sharing, for instance, linear regression, 99% of the on-chip traffic is eliminated. On average, across the 28 benchmarks that we looked at, the 16 cores, we actually see a 37% on-chip traffic reduction. So to summarize, what we've presented to address a couple of challenges is an application-tailored hardware coherence approach. And the challenge that we're trying to address is that in order to scale cache coherence to large core counts, we need to make sure that the directory implementation is efficient and that inter-core communication is streamlined to reflect actual application behavior. We observed that applications exhibit inherent patterns in locality and sharing behavior of cache data, and based on those observations, we were able to design a set of complementary protocols, Space and Protozoa, that tailor the metadata storage and the coherence traffic to match each application's inherent sharing behavior and thereby streamline the overall design. So any questions, we'd be happy to answer them.
Thank you, Sandhya, for that excellent description of your work and for submitting the work to IEEE Computer. I do have a few questions. Going back to the first part of your talk, in the work on the space project, my understanding after hearing your talk and reading the paper was that in some instances you have a conservative representation of the sharers or the sharer vector, where it's possible that the directory thinks that a particular core has a copy of the data block when it does not. So how is that issue handled in your protocol?
Arvind, do you want to take it?
In our case, we just send back something akin to a NAC, which is that, we don't have it. The core doesn't have it, and the system has to recover from this in some way. This is very similar to what traditionally has been tried out in protocols such as the SGI origin, where the exclusive state is not known for sure. The directory could forward a message and then find out at one of the L1s that the data is actually not there, and then the directory has to recover in some ways. There are two possible ways in which you can recover. One is observe the fact that the block doesn't exist in the L1 and then send the message back, which makes the protocol 4-hop, which is what we do to save bandwidth. Or speculatively send it from the directory anywhere to start off with, which is what the origin does. That makes the protocol more like a 3-hop.
Thank you. So I had another question on the space project, or the space part of your talk, which is you're adding a level of indirection to this pattern directory. And I was wondering if you'd done any experiments or you had any insight to offer on any changes in clock speed or directory latency that result from this additional level of indirection.
Well,
so I can take this, or do you want to take this on you?
Go ahead.
So in our evaluation schemes, we used a mesh-based multi-core. So we tiled the directory, or caches, shared caches essentially tiled across. And we maintain the space, we compress the patterns only within a given tile. So we don't try to compress patterns across tiles. So there is a space directory or a pattern table per tile, okay, which obviously there's a trade-off here. One is you can only observe common patterns within the cache block that are in a tile. You can have, and so in our evaluation, it's the latency add-ons are not significant. So the latency effects of the directory would not directly impact performance. Obviously, this comes with the trade-off that there may be common patterns across tiles that you could have possibly observed and compressed, but we don't. Alternative designs do exist where the question is how many space pattern tables you dedicate for for the whole multi-core, possibly. In which case, you would need networks that connect up the tiles to the directory's pattern table itself, and the latency would have to be taken into consideration. This is an open problem. We have not, by far, solved it by any means.
I also want to emphasize that the directory and the directory table is in the path of an L1 mix rather than in the critical path of the processor. So it should have minimal impact on clock speeds.
Great. Thank you both for that answer. One last question on the Protozoa project. There's been some work over the past few years on not caching the data that's returned from the directory on an L1 miss and simply loading it into a register because the spatial locality of this data is not high, and it's not worth polluting the L1 cache with the block. I see that in Protozoa, with the variable size blocks, you're obviously getting the benefit the reduction in pollution and also the reduction in coherence traffic. I was wondering if you had considered an extension to Protozoa where you went all the way to you already gone all the way to a single word being cached, but going further to simply loading that word into a register, and whether you had any thoughts on whether that would provide improvements or not.
Right. So what Protozoa does is eliminate traffic due to false sharing when data fits in the L1 cache. And I think the optimization in your papers and others will additionally target true sharing. So eliminate the need for an invalidation round trip in the case where data is loaded into the register and immediately modified by somebody else. We've actually, I think there is a possibility for synergy of these two designs, but we've also looked into other protocols in the past. A prior student of mine, Himayat Hussain, has done some work looking at how to essentially get the data to where it is needed based on the specific sharing behavior exhibited. In other words, make sure that directory traffic as well as, directory update traffic as well as data traffic moves to where the data is needed next. In that work, we didn't actually look at avoiding the cache altogether. It is certainly something that's complementary and something we could look at.
Thank you. Yeah, I do think that there's a synergy, between the uncache block projects and work in the past and your work on Protozoa. Thank you again for an excellent presentation and for submitting your work to IEEE Computer.